For now, we set clear boundaries in place. We do not provide one-to-one support, and the safeguarding consent should be escalated to appropriate external services where needed. For upcoming tutoring masterclasses and webinars, you must follow our guidelines. These measures are in place to protect both students and staffs while MDN safeguarding framework is being finalized. Microphones should remain muted. Cameras should remain off, particularly under 18s. And as we are all year 12s and year 13s, most of us are still under 18s. If you're under 18, please let a parent or guardian know that you are attending the session. By joining our sessions, you agree to follow everything above. And today, being your tutor for today's masterclass, I would be asking questions as well as answering your questions in the chat box. Please do well to message, and I will surely answer your question. And I hope we get to the last point of today's lesson. Thank you. We're going through exponentials and logarithms, and the first step to go here is to go through the basic part of logarithms. So the first here is, the inverse of many mathematical operations. We can undo an addition by 2, for example by subtracting 2. For example, if we have here where we have multiplication, the inverse of multiplication is therefore division, so we have x divided by 3. The inverse of positive here is negative, so we have it as negative 3x. Inverse of squared is square root of x. The inverse of raised to the power of 5 is raised to the power of 1 over 5, or we do have raised to the power of 1 over 5, or 5 root x, like this. And now, this is where it gets interesting. When we have 3 to the power of x, the inverse of this is log 3x, log base 3 of x. This is an exponential function. And log 3 base x is a logarithm, which is the inverse of 3 to the power of x, is log 3x. So now, when we are interchanging between exponentials and log form, log base a of n is equivalent to this. This is an exponential function, and this is a log form because we have the log there, so this is a log form. It's simply saying 3 squared is equals to 9, implies both ways for log 3 is equals to 9. So now this is exponential and this is the log form. So now there are two ways to convert from logarithms to exponential. We have the method one, which is using the missing power, and method to do same operation to each side of the equation. So going through with using the missing power method. Now, if you are trying to convert from this place to an exponential function, how are we going to do that? Now, this is saying log base 2 of what power are we going to have to get 8? And we know 2 times 2 times 2 is equals to 8. That means 2 cubed is equals to 8. That means here we have log base 2 of the power 3 is equals to 8. So that implies that 2 cubed is equals to 8. So in here we've converted from logarithms to exponential function. An interesting fact about this, and the way is very easy for me to convert from logarithms to exponential function, is I make this 8, I make it just a number 8 on its own, and I bring this 2 here, I make it have 3 as a power. That's 2 to the power of 3, because there are some instances where we don't have, for example, the way we have 2 to the base 3 is equals to 8. Some instances, there is no a specific whole number power that will be equals to whatever value we have here. So that's a good method I use and works every time. Now, the method 2 here is doing the same operation to each side of the equation. Here, formula, they add 3x plus 2 is equals to 11. They subtracted 2 from both sides. And that's how we have 3x is equal to 11 take away 2, which gives us 3x is equals to 9. That's the way we can also do this. Now, to do this, log of what power is very similar to the other one, would give us 8. The same thing as 2 cubed is equals to 8. So now we'll be rewriting this using logarithms. 6 squared is equals to 36. The first step to do here is to say log base 6 to what power will I get 36 for? So we know the power here is equals to 2. Is equals to 2. So that implies that log base 6 to 6 is equals to 2. That's a very simple way of doing it. So the power of base that gives me 36 is 2. Similarly, I can do that for the b part. So b log base 2 of what power would give me 128, and I know 2 to the power of 7 is equals to 128. So that implies that log base 2 to 128 is equals to 7. For the last bit, see, I can as well use this method here for C, where I take log of both sides, as I said earlier. So we're taking log of both sides. So taking log of both sides here, I have 64 to the power of half is equals to 8. When I take log 64 of both sides, and the reason why I'm taking log 64 of both sides is because 64 is the one with the power of half. So that when I take log 64 of 64 to the power of half, I will just have half left is equals to log base 64 to the power to 8. So that means I have log base 64 to 8 is equals to half. And that's how I did this one. So if you look at it using the method I said earlier, where I can convert this back to an exponential function, and that can be done by where I make 8 on its own is equals to 64 just to the power of half. Whatever is here comes here and take this as a power, and that is how I can do that. So with that said and done, I can move on to converting logarithms into exponential functions. So the A part, let's quickly rush through this so we can get to the real questions. Log base 3 to 81 is equals to 4. Using the first method, this implies that log base 3 of what would give me 81, and I know 3 times 3 times 3 times 3, which is equals to 3 to the power of 4 is equals to 81. That implies I have log base 3 to 4 is equals to 81. That also implies that log base 3 to 81 is equals to 4. That means 3 to the power of 4 is equals to 81. Yeah. And it can also be done in the simplest way I talked about, where I make 81 on its own, and 3 taking this as a power is equals to 3 to the power of 4, which is otherwise the same as 3, 4 is equals to 81. That said and done, I can move on to the B part, where I have log base 2 of 1 divided by 8 is equals to negative 3. And for this one, I can as well take 2 to be the power of this. So 2 to negative 3 is equals to 1 over 8. And I can prove this by saying 1 over 2 base 3 sorry, 1 over 2 cubed, because 2 to the negative 3, this negative makes it have that fraction bit, is equals to 1 over 2 times 2 times 2, which is equals to 1 over 8. Therefore, this is correct. C, log 100 is equals to 2. When we are given a logarithm without a base, that means the logarithm is to the base 10. So for this one here, I have log base 10, 100 is equals to 2, making 10, take the 2 as its power. Why is it? So I have 100 is equals to 10 to the power of 2, which 10 to the power of 2 is 100. So this is my equation there. Moving on, without using a calculator, find out the value of the following. This is just a quick fire question that we can quickly go through. And here, log base 5 to 25. Here we do have, we are not using a calculator, and this is not even an equation because we don't have equals to there. So the best way for us to do this is using our first method, where we find the missing power. So now log base 5 of what power will give us 25, and we know 5 squared is 25. That implies that the answer here is 5 squared is equals to 25. So answer here is 2. Similarly for this, 3 to the power of 4 is equals to 81. So that means log 3 of what power is equals to 81. That implies we have 3 to the power of 4, which implies our answer here is 4. So this is equals to 4. This is equals to 2. For the C part, log base 2 of 32, 2 log 2 to the power of what gives me 32. 2 to the power of 5 is equals to 32. So 2 to the power of 5 is equals to 32. So my answer here is 5. So these are very similar with the D part. Or okay, going to the D part, I know log 10 to the power of what gives me 1,000. So log 10 to the power of 3 gives me 1,000. So of course I know 10 to the power of 3 is equals to 1,000. And this is even an exponential function. So this is equals to 3. Now for this bit where we have 1, we know any value to the power of 0 is equals to 1. So because I have a base 4, I can alter the question where I make 1 is equals to 4 to the power of 0. So this is the same thing as log 4 to the power of 0. So the log 4 to the power of what will give me 1, which is the same thing as log 4 to the power of what will give me 4 to the power of 0, and that is 0. So my answer here is equals to 0, is equals to 0. There is even a shortcut method for this, and we'll be going through that in the logarithms law. For the last one, when we have log 4 of what power will give me 4, they are actually the same thing, so that's just to the power of 1. So our answer here is 1. And okay, we'll go through that here. So to the fraction bit of the question, I can as well skip this. Okay, let's do this. So because these are very similar and I would like to rush quick through this. Now this is the same thing as log 2 16 negative 1. 16 is the same thing as 2 to the power of 4. So this is the same as log base 2 to negative 4. So now log base 2 of what would give me 2 to the power of negative 4. Here is like I'm saying 2 to the power of what will give me 2 to the power of negative 4. So our answer here is negative 4. So now log base A of what will give me A cubed. So cube here is equal to 3. My answer here is 3. Similarly, for this one, we can never have an output when we have -1 in a logarithm. We would never get an output. You can as well put that in your calculator. That will probably give you non-existing or undefined. Like, it doesn't exist. It doesn't exist. So this doesn't exist even on a log graph, as we'll go through that now. Doesn't exist. Now, these are the logarithms. Few law of logarithms, because when we have log base a to the same value, like a, when we have the same value, this is equals to 1. That is equals to 1, and that can be proved when we say log base a of what would give me a. That's simply saying a1 is equals to a. So definitely our box here is equals to 1. So it's just a law of logarithm that can be proved, and we should know that by heart. When we move on, okay, for example, if we this is the same thing as talking about log base 5 to 5 is equals to 1, log base 2 to 2 is equals to 1. Moving on to this, as I said earlier, anything to the power of 0 is equals to 1, and the same thing as saying log a to the power of 0. So with this, I'm just talking about log of a base what would give me a to the power of 0, and here is very visible that our answer is equals to 0. So that means log base a to 1 is equals to 0. We can as well, when we do this, I would like to come back to this one to address some certain things there. Now, when we have log base a to something like this, where we have the same base with a power, we can bring the power to become x log base a to a, and using our law of logarithm, we know this is equals to 1. So we have x multiplied by 1 is equals to x. So answer is equals to x here. Now, coming back to this one here, since I have base a here and I have a here with the power of 0, I can say 0 multiplied by log base a to a. 0 times 1 is equals to 0. I've used my law of logarithm from here into this law of logarithm again. So the last one, this, when we have a log base a to x, is an inverse. These two are inverse functions. They are both inverse of each other. And this is equals to x. They both have the same answer. It's very rare we get a question that looks like this, but we can just know that when we have a logarithm question in this format, our answer here is x, which is an inverse of this. Now, logarithmic graphs. I can as well use my calculator to get the values of y here, but it's very good to show this without using a calculator. And the first step here, this is the graph of this graph here is a graph of y is equals to x. The gradient gradually decreases but remains positive. Log is an increasing function. As you can see it here, the green is an increasing function. So y is equals to log base 2 of x. And earlier on, we talked about the inverse of log here. The inverse of an exponential is logarithm. So that can be seen on the graph. The green graph is this, while this graph is an exponential graph. And we can see it's an inverse because it's a reflection on the y is equals to x axis. That's how an inverse works. a reflection. They're all an inverse of logarithm is exponential, and they are reflection of each other on the line y is equals to x axis. Now, drawing this green graph, we use this table here, and y is equals to log 2x. So this is the graph of y is equals to log base 2 to x. Now, I can fill out these y values by just putting in when log base 2 to 0.25 is the same as log is 2 to 4 1 over 4, which is the same as um, log base 2 to 0.25, similar log base 2 1 over 4. Here I can try to manipulate this 1 over 4 to have a power a base of 2, right, where this is equals to log 2 1 over 2 squared, which is 2 negative 2 negative 2 log base 2 to 2. I used my law of logarithms. So this negative 2 multiplied by 1 is equal to negative 2. And that can be done for the rest of the values in this similar method. And you can as well use your calculator. But I would advise you use this like solving it normally to put the instinct of knowing how to do this. So if I solve this continuously, I will get negative 1, 0, 1, 2, 3. Now we can see that this here is similar to this graph here. When we have 2, when x is 2, y is 1, when x is 4, y is 2, when x is 8, y is 3. Similarly with the negative axis. So basically, this is an increasing function here, as they've said here, and the reason why we have this here is to understand that the log of base anything of 1 is always going to be 0. And what I mean by this statement is that when we have y is equal to log 2, log base 2 to x, when x is 1, which is the same thing as log base 2, 1 is the same thing as 2 to the power of 0. My law of logarithms, so 0 can come here, log base 2 to 2. I know when we have the same value of our base to our actual value, it's the same thing as 1. So 0 multiplied by 1 is equal to 0. So that's why we have when x is 1, y is 0. So the logarithm of base of anything of 1 could be log base 2. It could be log base 5 of 1, log base 2 of 1, log base 8 of 1 is always going to be 0. And that's why we have our graph here. So we have a vertical asymptote where x is equal to 0. So when x is 0, that's the, because asymptotes basically, it's a line at an instant where the graph would never meet or touch. That is just understanding of what an asymptote means, because our line, a vertical asymptote at when x is equal to 0. So when x is 0 here, this line, this graph of this green graph would never touch the line. It will always get closer, but would never touch the line. We could have negative 0.000005, negative 0.0002, but would never be 0.0 exactly. It would never. That's what an asymptote is. So with a calculator, this is just learning how to do logarithms and natural log. So before I go deep into this, I would like to explain what a natural log is. Or okay, let's go through the logarithm part. So when I use calculator to get this, as before using calculator, I know that log base 3 of what value is 7. And as I said earlier, there are some certain instances where we don't have a whole number. We don't have a whole number here. Can never be an whole number. But decimal. So the interesting part of this is we can use a calculator to solve this, and using my calculator to get the value of the power raised to power 3 to the power of what 3 to the power of what would give me 7, and that gives me 1.77 to 2 decimal places. Same thing as here, we have negative 0.75 to 2 decimal places. Now we are getting to the interesting bits of logarithms. So there is something called natural logarithms. It works the same way as logarithms itself. They have similar or the same rules as logarithms. And it's very interesting. They work the same way, and yeah. So natural logarithm, when we have natural logarithm of e on its own, natural logarithm deals with Euler's number. Euler's number is basically 2.741 something something. So ln is a natural log of x, meaning log to the base e. It still works like log, but instead it's the log to the base e. Remember when I said log to a value without the base, it's the same thing as log a base 10 to 100. Natural log is the same thing as log base e to whatever value we have. So that's another style of logarithm. Now, so this is it. So imagine we have natural log of e. So that means we have log base e to e, which is the same thing as when we have this same one, using my law of logarithm. So natural log and logarithms, they all what is natural log is actually logarithm. It's even said in the statement there. So now natural log of 10, I can put that into my calculator and I can get my value. And I can also say log base e to 10 is equals to what? I'll get the same thing, but it's easier to just put natural log in your calculator, and that gives me natural log of natural log of 10. That's 2.302585.093, and that's 2.30 decimal places. So that is that for that. Log base 100. I never knew this was even there. So log without a base is a base 10 by default. So this is log base 10 to 100, which is the same thing as log base 10 to 10 squared. Law of logarithm, 2 times log 10 to 10. Log 10 to base 10, they have the same base, the actual value that's 1. So 2 times 1 is equal to 2. So that's my final answer for that. So more laws of logarithms. Laws of logarithm. They're easier to understand and they're also easier to misuse. So the interesting fact of how I feel like it's very easy to understand it is you can only when you have a positive value, when you have positive between two logarithms and they have the same basis, because if we have log a to base x plus log base a, sorry, let's say b, for example, so y, this is not equals to log xy, because the base here will be so absurd. Because the reason why is not the same is because of inconsistent bases of a and b. They must have the same thing, just like this and this, to be able to work out as this. So we have the positive becomes multiplication, the negative becomes division. So there are actually steps we can take to prove this. We can prove this, and we would be proving it. So, because of this law of logarithm we talked about earlier, this k can come here and multiply just as this and log base a to x. So the summary of this is that when we have positive between two bases, it turns to multiplication. When we have negative, it turns to division. Special cases. When that means we've talked about this, when we have the same base, so the actual value is equals to 1, given that a must never be 1. A must never be 1, but a can be greater than 1. And if you ask me why a should never be 1, that means you're talking about if a is 1, here you have a different solution. I will come to that soon. Another key fact about this I will add here is a to the power of 0 is equals to 1, which is the same thing as b to the power of 0 is equals to 1. So, coming to this one here, I've proved this earlier, but it's good to go over it again. Log base a to 1 is the same thing as a to the power of 0, which is equal to 0 times log base a to a. And using this law of logarithm here is the same thing as 0 times 1, which is equal to 0. Moving on to the last bit of this is equals to this, and that can be proved by, it has already been proved, when we have log 1 over x. 1 over x is the same thing we're talking about. Let's say 1 over 2. This is the same thing as 2 to the negative 1. So that's why we have x to the negative 1 here. This can come here and multiply. We have negative log of x. And if you ask me, without no base here, I know 10 is here, 10 is here, and 10 is here. So laws of logs can be proved. Now, how are we going to prove this? We need to rewrite in exponential form. So when we rewrite this in exponential form, now proving laws of logarithms, in this step, it's very good if we understand how to convert from exponentials to logarithms, as well as logarithms to exponentials, as we're making good use of that in this process. Now let's get into it. Now, letting log a is equals to b and this equals to c. Now, proving laws of logarithms. Here, we need to understand how to go from exponentials to logarithms, as well as from logarithms to exponentials, as though we useful and will be needy in this aspect. So the first step to go through here is, if log a is equals to b, log this is equals to c, that means I can rewrite this as x is equals to a to the power of b, y is equals to a to the power of c. If you don't understand how I did this, you can go through the beginning of the video. That was explained thoroughly there. So xy, that means I'm multiplying these two together here. It's the same as saying a to the power of b multiplied by a to the power of c. And I know that I can convert this back into logarithms, because my final destination, my final achievement should be this, which is in logarithms. So I need to convert this back to logarithms. So before that, xy, using law of indices, a, because they have the same base, is same as b plus c, law of indices there. When I take log of both sides, the power of a that gives me xy is b plus c, because when we have a, b plus c is equal to xy. So taking log of both sides is as well as saying log a to the power of what? Xy. So and I know is b plus c, so this is equal to b plus c. So log base A, so xy is equal to b plus c. And my b here was log base A to x. So log base A to xy is equals to b. Here is log ax plus c is this. So log base A to y. And that has proved this. Proven. Now, to the next stage is very similar in the same way, so I'll just go through it quickly because I would like to go through some difficult logarithm and exponential questions at the end of the video. So now, at the end of the lesson, sorry. So this implies that x is equals to a to the power of b, y is equals to a to the power of c. X divided by y is saying a to the power of b over a to the power of c. That implies that x over y is equals to log over indices a, b, take away c. So taking log of both sides, log a x over y is equals to b minus c. And I know this is equals to b log base a of x minus log base a of y. Also, I can prove the last one. I can prove this through this. Now, log x to the power of k is like I'm saying, okay, for example, if I should say log a x to the power of 2, if I were told that this, I would know that definitely I'm talking about log a x times by x. Similarly, if it were to be log base 8x cubed, it's like I'm talking about log base a x times x times x 3 times. But k here, we don't know where k is ending, so we feel like this is infinite to k value. So basically, x to the power of k is telling me, is saying x times by x times by x times by x times by x. I don't know where to stop. All I know is continuous because I don't know what k is. So basically here I'm using the power rule. So I am multiplying here. I am multiplying this is so funny. I'm multiplying it by itself k times, because I don't know what k is, but all I know is I'm multiplying k times. So basically I am adding k lots of log. I am adding k multiplied by log a to x. I don't know what my k is, but I'm doing this several times in several k times. So several k times. Now this is where it gets interesting. So that means, because I know this multiplication is saying log base a to x plus log base a to x plus log base a to x k times. It's continuous. It's as well as saying k, the number of times it continues, k times by log base a to x. I don't know what this is, but I know this repeats k times. So this implies that this is k log base a of x, which is similar to saying this power comes here, multiplies it, and this remains. So that is the way that can be explained. Now, moving on. The important fact here, because I see most people mixing things up in terms of this, and here this is where it comes to. Do you know these are not equal to themselves? At first glance, it's giving a question mark of wait, I just explained that just now. But instead, the power of k here is not the power of the whole bracket. If it were to be log base a bx all to the power of k. Then this is equals to k log base a to bx. But instead, the k power is just on x alone. So my law here is invalid to be used here. So now to solve this, that's the question. To solve this, I can as well open my bracket first, like expand the bracket. And that can be done by log base a to b. Because there is a multiplication sign here, I know I am adding it up here. Plus log base a to x to the power of k. Now, I can use my law of logarithm. My law of logarithm. I can use law of logarithm to solve this part. So this is the same thing as saying log base a to b plus my k can come here, log base a to x. So basically, this is my answer, not this. So this is my answer. Now, write as the single logarithms. Now, the first thing I noticed was these three being the same as this 3 here. So I have a consistent base. Perfect. Then I can use my law of logarithm. Because this is positive, I know I'll be having something to do with multiplication. So this implies that log base 3 is same thing as 6 times 7, which is the same thing as log base 3 to 42. Now I don't have a log base here. I don't have a base here, and I know 10 should be there. I can do this by even ignoring the 10. Log 15 negative, that means I'm going in with division here, divided by 3, that's equals to log 15 divided by 3 is 5. So log 5 is the same thing as saying log 10 to the 5, which is the same thing as saying log of just 5. We are mathematicians at this stage. So going on with the C part, 2 log 5 base 3. Now I'm so glad we have 5. Perfect. They are consistent. Now, I must make sure I am able to simplify this, because I cannot just jump and say, oh, okay, log 5, 2 plus 3. Okay, let me write the question out. It's very wrong for me to say 2 plus 3, like 2 log 5, log base 5 to 3, plus 3 log base 5 to 2. It's very wrong for me to say, oh, 2 plus 3, oh, that's 5 log 5, 3 times 2, 6. This is a very wrong way to solve mathematics, or even logarithm at this stage. The best way for me to do this is simply by saying, oh, okay, this is the same thing as 2 log 5 base 3, same as, oh, when I have log base 5, the 2 is saying 3 squared, because when I put the 2 back, I'll get the same thing. Similarly, plus log 5 2 cubed. Oh, I just use law of logarithm. Perfect. Then I can go on log base 5, 3 squared is 9, plus log base 5 2 cubed should be 8. This is saying, oh, positive. Then I'm having something to do with multiplication. So that's log base 5, 9 multiplied by 8. And 9 multiplied by 8 should give me 72. Yeah, perfect. Log 5, 72. What I just did here is similar to this, and I would just like to do the last one because that's a natural log and one of the interesting parts of logarithms. So for the E part, 3 natural log of 4 plus 3 natural log of 2. I cannot use the way I did this one, what I said here. I need to break it down. With this, I can even change my natural log to log E to make it look more like logarithm on its own. So now that implies we're saying 3 log base E to 4 plus 3 log base E to 2. So this is saying log base E to 4 to the power of 3. Same thing as saying 3, what can come back here, plus log base e to the power of 2 cubed. 4 to the power of 3 is 4 times 4. 16 times 4 is 64. So that gives me log e to 64 plus log base e. 2 cubed is 8. Because I have multiplication here, I know I am dealing with something that looks like I have addition. I know I'm dealing with something that looks like multiplication. So that's log base e to 64 times by 8. That's equals to 64 times by 8. 64 times by 8, 512. So log base e to 512. Log base e, we know, is natural log of 512. And I can as well input that in my calculator. 512. So that will give me decimal, and I don't want decimal. So I can leave my answer. And I can sometimes we can be asked to leave our answer in decimal forms, or in its exact form, or in a simplified form, and this can actually be simplified. And the reason why I know it can be simplified is because 512 is the same thing as, let me check if I'm right. Yeah, it's the same thing as 2 to the power of 9. So as I'm saying, natural log of 2 to the power of 9. Using law of logarithm, this is the same as 9 natural log of 2. It looks more beautiful this way. So write in terms of log base a to x. Write in terms of this. So we have this. So the a part here, we have multiplication. This is division. Yeah, perfect. So the a part, I know I have multiplication, and I can split it back to addition. So that means log base a to x squared plus log base a to y plus log base a to z cubed. Law of logarithms. The powers can multiply the main log itself. It implies that log 2 log a base a to x plus log base a to y plus 3 log base a to z, and that's my final answer in terms of log a base to x. It meets this, and meets this. So for my b part, log base a to x divided, I know this means I am what? Subtracting. This means addition. This I am doing both addition and subtracting. Here I am doing just division. So here I am doing just this one, division, subtraction. So no log base x to negative log a to y cubed, which is the same thing as log base a to x minus law of logarithm. This 3 multiplies the whole logarithm function, and this is my answer in terms of log a base y and log a base x. For my C part, this is a little bit complex, but it's still very easy to work with. And here, log base a. When I first of all use my division, x cube root of y minus log a to z. This is still multiplication, so I need to turn it to, so log base a of x plus log base a of root y minus log base a of z. This is still not in just y form. I know this is the same thing as log base a to x plus log base a to y half minus log base a to z. This implies I have log base a to x plus my half can come here, log base a to y minus log base a to z, and that is in terms of this, in terms of this, and in terms of this. For the last one, it's similar to what we've been doing. Yeah, so I have My D part, I know this is just division, so that's subtraction. X minus log A4. Law of logarithm is used here. Log base A to X minus 4 log base A to A, and this means 1. That implies I have log base A to X minus 4 times 1, which is equal to log base A to X minus 4. So that's perfect. So I'll go through. I really want to go through the questions, and okay, we'll do 2 questions from here, and let me quickly go over the mistakes to avoid. As I said earlier, it's very easy to follow the law of logarithm, as well as it's easy to go against the law of logarithms. And here is an example. Now, because I have log AB plus C does not equals this. Instead, this on its own is equals to log A, because I have positive here between consistent bases. A, B multiplied by C, which is equal to log base A, B, C. Not this. Not this. This is not equals to this. As well as when I have this, because this 3, it cube roots the whole log function. This is not equals to log base 2x cubed. It's only when this is this, that's when we have this being equals to this. So basically, it implies that log base 2 to x cubed is equals to 3 log base 2 to x, but log base 2 to x cubed is not equals to 3 log base 2 to x. The power must be on the input, here the x, but here the power is around the entire log function. Simplifying log expressions. Many questions, particularly in year 2 integration, will ask you for your answer in simplified exact form. They usually ask for a natural log of 2 or a plus b natural log of c form. And we can simplify to the form this. I would like to just pick out, okay, I will do D and let's go with some fractions, C and D. Now, the first step here, C, natural log of half plus natural log of 8e squared. To make things easier for this explanation, I will convert from natural log to log e, and as well as do it this way. So now, making it easier, I know natural log is the same thing as log of e. I know that. So that means natural log of half is the same thing as log e to half, which is the same thing as log e 2 to the negative 1, which is the same thing as negative log base e to 2. I use law of logarithms. This negative half multiplies it here, and that's how it becomes negative log base e to 2. As well as natural log of 8e squared. I know for this one, natural log of 8e squared, the same thing as saying log e 8e squared is the same thing as log base e to 8, because it's multiplication that is here, multiplication sign here. I know this is log base 8e plus log e squared. This is the same thing as log e to base 8 plus 2 log e to e. And I know this is equals to 1. So that implies the log e8 plus 2. And I know I can remember my question was this plus this. So that implies I have negative log base e to 2 plus log e8 plus 2. Don't forget, I know that my natural log is equals to log base e because my questions want it in natural logarithms. That was the question. So here, replacing every natural logarithm here with every log base e with natural logarithm. I have negative natural logarithm of 2 plus natural log of 8 plus 2. I can rearrange this by saying natural log of 8 negative natural log of 2 plus 2, but it's still not in this form. I just want it to have only natural log of 2. The easiest way, I could have even done it at this stage here, but the easiest way to do this is saying natural log of 2 cubed negative natural log of 2 plus 2. Law of logarithms, we have 3 natural log of 2 negative natural log of 2 plus 2. Because I have natural log of 2, natural log of 2, I can take 3 negative 1. This is the same thing as saying 3x minus x, which is equal to 2x. This was just an explanation. So that implies 3 minus 1 is 2 natural log of 2 plus 2, which is similar to a plus b natural log of 2. Sometimes we can be asked to give the values of a and b, and here a 2 natural log of 2 plus 2 is similar to b natural log of 2 plus a, where b is equal to 2 and a is equal to 2. So I would like to go to the D part. Yeah, the D part. What is okay? We'll try to manage the space as well as going along. Natural log of 2 root 2 minus 16 root 2 plus 2 natural log. We're doing this. So now, natural log of 2 root 2. I would go through this without converting from natural log to log base e. That sounds more interesting. And so natural log 2 base 2 is saying natural log of 2 multiplied by root 2. So this is the same thing as saying natural log of 2 plus natural log of root 2. And this is the same thing as saying natural log of 2 plus natural log of 2 to the power of half. Natural log of 2 plus half natural log of 2. Interestingly, I also have natural log of 16. So natural log of 16 over root 2 is saying, because I want everything in terms of 2, so the easiest thing for me to do here is saying natural log of 16 minus natural log of root 2. Because I have division, it surely turns to negative. Natural log of 16 is saying 16 is the same thing as 2 to the power of 4 minus 2 to the power of half. This is the same thing as 4 natural log of 2 minus half natural log of 2. 2 natural log of 2 root 2e. Now this gets okay. If you look at this well, this 2 here multiplies the whole function. So the easiest thing for me to do is 2 multiplied by natural log of root 2e. I can separate the ones inside first to make it easier. So 2 natural log of root 2 plus, because I have a multiplication sign here, natural log of e, which is same thing as 2 natural log of 2 to the power of half plus natural log of e, same thing as 2 half natural log of 2 plus natural log of e. So when I expand the bracket, the first one, these 2 cancel these 2, so I just have natural log of 2 plus 2 natural log of e. Now I just need to combine all using my negative and addition sign. So the first one, natural log of 2 root 2, so I have natural log of 2 plus half natural log of 2, subtract this 4 natural log of 2 minus half natural log of 2, and add the last one here, natural log of 2 plus 2 natural log of e. Now I just need to simplify to come to a conclusion. Before simplifying, this natural log of 2 here, and this one becomes 2 natural log of 2 plus half natural log of 2 negative 4 natural log of 2 plus minus times minus gives plus half natural log of 2 plus 2 natural log of e. So that implies that 2 natural log of 2, so 2 plus half plus this half plus half gives me 1. So that is this plus this is 1 plus this, making it 3 minus 4 natural log of 2. So combining this together, I would simplify my answers to, the first one is 2 natural log of e, as explained in, when did I explain it? 2 natural log of e is the same thing as just 2 because I have log base e to e. So I know this is 2. And half plus half is 1 plus 2, 3, negative 4, that's negative natural log of 2. So this is my answer in the form of a plus b natural log of 2. Very interesting. So your turn is this, and I would like to go through this one because this brings together all the knowledge, all the law of logarithms, exponentials, and everything we did to just a question. So now, given that 2 log base 2 to x plus 15 minus log base 2, I'm so glad my bases are consistent in the first place, so I can apply the law of logarithms that deals with negative going to division. So the first thing I need to do here is to transfer my 2 back here. So now, show that this, I know that I need to simplify. I need to turn my logarithm into a simple equation. So now, a log base 2x plus 15 to the power of 2 negative log base 2x is equal to 6. Yeah. So, law of logarithm implies that log base 2 x plus 15 squared divided by x is equal to 6. Here, I can use law of logarithm. And as I said earlier, I can make 2 take 6 as its power, so we have 2 to the power of 6, and I make this sit alone, so x plus 15 squared divided by x. So x multiplied by 2 to the power of 6 is equal to x plus 15, x plus 15. So expanding this bracket, I will have it as 2 to the power of 6 should be, how much, 2 to the power of 6, 64 x squared plus 30x plus 225. Oh my days, is looking so similar. So I have x squared plus 30x, take negative 64 of both sides. So I have negative 64x plus 225 is equal to 0. So that implies that x squared negative 34x plus 225 is equal to 0. So hence or otherwise solve this equation. So to solve this equation, that means I'm looking for x. So I can solve this quadratic equation as my solution. And you can just input that in your calculator or get two values using your calculator, and that should be, so 1 negative 34 225, so that's 25 and 9. So I have x negative 25 and x negative 9 is equal to 0. So x is equal to 25 or x is equal to 9. Now we need to check if both values will actually work for our logarithm, because I know that a negative value does not work. So if I should have a value that when I put it inside this and this, if I should get a negative value, that means that x value is invalid. So I know that when I put 25 plus 15 here, I'll get a positive value, and here is a positive value. When I put 9 plus 15, I'll also get a positive value, and here I'll get a positive value. So both values would not make a negative. So x is equals to 25 or 9. This statement could probably be a mark because you need to show that. Now, before I go into solving equation with exponential, I would love to do this question. I know when I say something like this, well, if the value by its side, I need to bring it back as a power. So I know log base 3 to x plus 11 squared is equals to 4 plus log base 3 x minus 5 squared. Now, I can go on to expanding, but it's easier, make it more simple without expanding so much. So I can subtract from here. I can subtract log 3x minus 5 squared from both sides. So I have log base 3 x plus 11 squared minus log base 3 x plus 5 squared is equals to 4. Law of logarithms, because I have negative, so that's division. Log base 3x plus 11 squared divided by x plus 5 squared is equals to 4. So this 3 comes here and take it as a power. 3 to the power of 4 is equals to this comes down x plus 11 squared over x plus 5 squared. There are two ways I can do it. I can go on to expand it. I can as well take square root of both sides, where I multiply both sides power to half. I think it's easier to multiply both sides power to half, or I expand it. So even expanding it, let's expand it. So I know this seems as 3 to the power of 4 x plus 5 squared is equals to x plus 11 squared. 81 x plus 5 x plus 5 is equals to x plus 11 x plus 11. So 81 x plus 5 x plus 5 x squared plus 10x, that's 20x, no, 10x plus 25, so x squared plus 10x, is that right? Yeah, x squared plus 5x 10x plus 25 is equals to x squared plus 22 plus 821. This is basis of quadratics. I can solve this. That's 81x squared. Open the bracket because I just have limited space here. And I know my answer my equation at the end should be 80x squared negative 832x plus 1904 if I'm right. And I'll get two values for this. X is equals to 7. Let me try that in to see if I'm 80 negative 832 1904. Oh no, 1904. So I have x is equal to 7 or x is equal to 3.4. Now, I need to see if both values would not give me a negative values. Now, when I put 7 here, I will get 7 minus 5. That's a positive value. When I put 7 here, I will get 7 plus 11. That's a positive value. But when I put 3.4 minus 5, I'm getting a negative value. And remember, a negative value into a logarithm does not exist because it has a vertical x is equals to 0 asymptote, as we saw on the graph previously. So this value would give me a negative value, but this is so therefore only x equals to 7 gives a negative gives a positive value for logarithms. Now as well what we did for this 25 on 9 here, and that was perfect. So I would love to go into pseudo quadratics revisited. I'm very sure you'll have seen something similar with this. This is just quadratics in log forms. Is there anything more difficult than that? and I would love to do one of this. Now moving on, let's go through one of this. Yeah, let's do this one here. Giving your answer to 3 decimal places. I know I'll be having an answer that deals with decimal numbers. Solve 3 to the power of x plus 1 is equal to 3 to the power of 2x negative 4. When we have a question like this, they can give you in the various formats. Just know this is a quadratic formula, quadratic equation in disguise. So now we'll try to manipulate this to give us a quadratic. Now, 3x plus 1, law of indices. What do we know about law of indices here? I know when we have 3x plus 1, it's the same thing as 3x multiplied by 3. This is law of indices. This is not even logarithm here. Which is the same thing as 3 multiplied by 3 to the power of x. Now, so I'm saying 3 multiplied by 3 to the power of x is equal to 3x squared minus 4. So I can definitely replace this with I can replace this and this with a random letter like y, z. So I can say let z equals to 3 to the power of x. So 3 multiplied by z is equal to z squared negative 4. 3z is equals to z squared negative 4. So z squared negative 4 minus 3z is equal to 0. Z squared negative 3z negative 4 is equal to 0. So z is equals to, using my calculator, I would get 4 or negative 1. So if 3x is equal to z, so that means 3x is equal to 4. So log base 3 to 4 is equal to x. So I'll get this using my calculator. That's 1.26223 dp. Or 3 to the power of x is equal to negative 1. So log base 3 to negative 1 is equal to x. Remember, log of negative 1 does not exist. So undefined. So this is my only answer. And that goes for this. Without going too deep into this is the same thing as 5 2x. Because this is minus, so that's divided by 5 to the power of 4, which is equal to 5x2 divided by 5 to the power of 4. So I can replace this in the equation. While this here is 5x multiplied by 5 to the power of 1. So 5 multiplied by 5x. So this, we have 5 to the power of x. 5 to the power of x can be replaced and be solved using quadratic method. So rushing through natural logarithms and we'll do the pseudo quadratics, and that's where we'll be stopping for today's lesson. So the inverse of e to the power of x is y natural log of x. So we know inverse of an exponential function is logarithm that is similar to e to the power of x is as an inverse of natural log of x. Natural log of e to the power of x is saying log base e on its own, e to the x. Law of logarithm, x log base e to e is equals to law of logarithm again, x multiplied by 1, so that's x. E natural log of x is equals to x. And that can be solved when I say, okay, it seems to say log base e to x, which is x. Solve e to the power of x is equals to 5. I can take natural log of both sides. So that's natural log of e to the power of x is equal to natural log of 5. Natural log of e to the power of x is x, as we've said earlier, so x is equal to natural log of 5, and my calculator will solve it from that. Similarly, 2 to the natural log of x is equal to 5 take away 1, that's 4. So natural log of x is equal to 4 divided by 2. So natural log of x is same as log base e to x is equal to 2. E takes this as a power, so x is equal to e to the power of 2, and my calculator gives me my final answer, or can leave it that way. So now going to pseudo quadratics. Yeah, before going to pseudo quadratics, I would love to solve this one. So enlighten us more about this. So now solving this, so I know there's a multiplication sign between both here. So 2x multiplication sign x plus 1 is equals to 3. I can say, okay, taking natural log of both sides and also using law of logarithms. So I'm saying natural log of 2x multiplied by x plus 1 is equals to natural log of 3. So this is natural log of 2x. Because of this one, but at the multiplication, I have addition. Natural log of x plus 1 is equals to natural log of 3. So this is the same as x natural log of 2 plus x plus 1 using law of logarithms because natural log of 3. So expanding my bracket, I know natural log of 3 of, I know this is equals to 1. So it's easier for me to say x natural log of 2 plus x plus 1 is equals to natural log of 3. And why do I know is equals to 1? Natural log of 3 is equal of is equals to 1 because natural log of is the same thing as log base to same thing, that's equals to 1. That's just a reminder there. So just x natural log of 2 plus x is the same thing as saying natural log of 3 minus 1. So factorize x out because we need to solve for x. Natural log of 2 plus 1 is equals to natural log of 3 negative 1. So my x here is natural log of 3 minus 1 by dividing both sides by natural log of 2 plus 1. And they said exact value. So this is my exact value here for x. Now, the last bit I would love to do here is solving pseudo quadratics in e to the power of x. So now let's do this one here. It works the same way as the one we did earlier. So now e to the power of x negative 2 e to the power of negative x is equals to 1. From here, it's a bit interesting because I have e to the power of x and I have e to the power of negative x. Now, for me to solve this, I can say, oh, okay, let's y equals e to the power of x. So that means if I say 1 divided by y is the same thing as e. 1 is the same thing as 1 divided by e to the power of x. So that means 1 over y is equals to e to the power of negative x. So I can replace both values there. So e to the power of x is y negative 2 1 over y multiplied is equals to 1. Y negative 2 over y is equals to 1. This is a quadratic equation because I can multiply both sides by y. So that's y squared minus 2 is equals to y. So y squared negative y negative 2 is equals to 0. So solving this using my calculator, the two values I should get. So we have 1, negative 1 and negative 2. So y negative 2, y positive 1 is equals to 0. So y is equals to 2 or 1. And I know e to the power of x is equals to y. So here, or e to the power of x is equals to 1. But I haven't solved for x yet. So the easiest part to do here is to take natural log of both sides. And I know natural log of e to the power of x is equals to natural log of 2. So x is equals to natural log of 1. So that those are my values. And the reason why I know e to the power of x natural log is equals to x is because this is equals to log base e to ex, which is equals to x log base e to e is equals to x times 1, which is equals to x. So that's why we have that as our answer. So thank you very much for today's session. And if you have any questions, drop it in the chat. Now we would like to go through it with you. These are questions I thought we were able to do, but time is on our side and we'll be stopping here. Thank you very much. And I really hope you do learn a lot from this and understand the key basics for logarithms. And once again, logarithm is just about it's about following the law of logarithms. If you're able to work with the law of logarithms, you would be able to understand how things comes by in logarithms and exponentials and natural logarithm. They work both ways. Thank you very much. Have a nice day.